Lots of people have to test pH. In fact, pH is the second most tested parameter after temperature. However, pH testing requires the use of sensitive equipment, and a lot can go wrong. There's a lot of different advice out there, which adds to the challenge. We've put together this comprehensive video to help everyone, from hobbyists to labs, test pH better. You don't need to be a chemist, but you do need to know a bit about pH. In technical terms, pH, or potential of hydrogen, is the hydrogen ion activity in a solution. It's measured on a logarithmic scale of 0 to 14, with 7 being neutral because the activity of positively charged hydrogen ions and negatively charged hydroxide ions is equal. At low pH values, from 1 to 6, the hydrogen ion activity is greater, so the solution is considered acidic. At high pH values, from 8 to 14, the hydroxide ion activity is greater and the solution is considered basic. There are 3 important things to know. 1, you are measuring tiny concentrations, which is why pH meters are delicate. Maintenance is key to accurate pH measurement, but there will be more on that later. 2, pH readings are affected by temperature, so you need to account for that. For example, a pH of 7 at 25 degrees Celsius may read differently at 20 degrees Celsius. 3, pH is a logarithmic scale. This means that a reading of 7 pH has a 10 times higher concentration of hydrogen ions compared with a reading of 6 pH. Small differences in readings can matter a lot. A pH measuring system consists of 4 main parts: a pH sensing half cell, a reference electrode half cell, a special meter to display your pH value, and your sample solution. Together, these form an electrochemical circuit that measures and displays the pH of your sample. Every pH meter has an electrode or probe. Until the 1970s, it was common practice to offer 2 half cells separately, a glass pH sensor and a reference electrode cell. Today, it's more common to use a single combined electrode that has both sensing and reference components. The combination pH electrode has a layer that's sensitive to hydrogen ion activity. Inside the electrode, there's a reference cell. The electrode creates a current that measures the charge on the glass tip compared to the reference solution. Keeping this bulb in good condition is vital. As a result of immersions in samples, a residue can form that stops the ions from binding or slows the process down. The binding layer can also get damaged. It cannot be repaired if it's damaged. Remember also that the electrode is a consumable. The binding layer will get less sensitive over time, and the electrode eventually will need to be replaced. This is true for all pH electrodes. The next part of the pH measuring system is the meter itself. The meter processes the voltage from the electrochemical cell and converts it to a meaningful measurement unit, pH. The final part of the measuring system, your sample, is the connection between the sensing electrode and the reference electrode. This connection allows the entire measuring circuit to work. pH electrodes come in a variety of designs, but they all have some key parts. When choosing a pH electrode, design considerations include the type and shape of the glass, junction material, and body material. First, the glass membrane. Hanna Instruments produces 4 different glass types covering a vast number of pH applications. General purpose glass provides the greatest response over the entire pH range and can be used for a wide variety of applications. Low temperature glass membranes have a lower impedance and are suitable for samples at lower temperatures and lower conductivities. Designed for extended use at elevated temperatures where glass impedance is known to decrease, high temperature glass offers a higher resistance, making it possible to obtain accurate results with excellent response times. HF-resistant glass is made for aggressive applications containing fluoride ions, which dissolves glass. This glass composition will ensure a much longer life for your pH electrode. Here's a sensing bulb on a simple tester, and here's what it looks like on a laboratory-grade electrode. The pH sensing bulb can come in a variety of shapes. Each shape serves a unique purpose. Spheric tips are recommended for general use in aqueous solutions. The round bulb geometry is the most common shape for a glass pH membrane and provides a wide surface area for a variety of liquid samples to contact. Conic designs are ideal for direct penetration into samples due to their pointed profile and geometric strength. These tips are well suited for samples ranging from soils and gels to sauces, cheeses, and meats. A flat tip geometry allows for a direct surface measurement of a sample. These designs are ideal for measuring the pH of skin, leather, or paper. The next aspect of the pH electrode is the junction. The type of junction used in the pH electrode is one of the most important design considerations when selecting the right sensor for your application. The junction is the electrical pathway between the sample and the internal reference half cell. This reference chamber contains an electrolyte solution, which diffuses through the junction into the sample. Any clogging of this junction may result in erratic and unstable readings. A porous ceramic frit is one of the most common junctions available for standard laboratory applications. The ceramic material is easily fused with the electrode glass and has a similar coefficient of expansion. An electrode may contain a single, double, or triple ceramic frit, allowing for enhanced electrolyte flow. Polytetrafluoroethylene, or PTFE, contains hydrophobic properties, providing one of the most chemically resistant junctions available. It's commonly used in pH sensors for industrial applications because of its chemical advantages and durability. A fiber wick junction, also known as a cloth junction, allows for a quick refresh when readings are erratic or unstable. An open junction does not have a frit. The electrode uses an exposed hard gel as the junction. This layer is silver-free. The open junction has a high flow rate, making it ideal for samples that would clog the junction of standard pH electrodes. Whether you're using a half-cell pair or combination electrode, the body material is an important consideration. The body of a pH electrode can be made of many different materials that may help to make pH measurements easier. The right body material will vary depending on the testing environment, the sample type, and the frequency of use. Glass body electrodes are ideal for any type of laboratory application. Glass is resistant to a variety of chemicals, it's easy to clean, and it transfers heat readily for a quicker reading. Polyethyramide is a high-performance, durable plastic that offers excellent resistance against aggressive chemicals. Rugged and resilient PEI electrodes are ideal for environmental and industrial applications in the field or on the factory floor. Polyvinylidene fluoride is food-grade plastic that stands up to a variety of cleaning chemicals and solvents. It's durable and has a high resistance to abrasion, mechanical strength, and resistance to fungal growth. Stainless steel is an extremely robust material that can withstand a wide variety of aggressive chemicals in the harshest of applications. Connection and communication is your final consideration when selecting an electrode. It's important to understand that not all electrodes connect to all meters. Some sensor connections are specific to a meter, brand, or manufacturer. Be sure to take note of your requirements when replacing or purchasing a meter and electrode. When choosing a pH meter, it's important to consider the sampling points at which you will be testing. Testers are great for spot checking or for use by hobbyists and are the least expensive. A portable handheld meter offers the mobility to test pH anywhere and may have data logging features that make field work easier. A high-performance benchtop meter, while the most expensive, is best suited for stationary lab use and most often offers advanced features and higher accuracy than other types of pH meters. Okay, you understand a bit about pH, how a meter and electrode work, and what to look for when choosing a meter for your testing. Now, it's time to make sure that you have everything you need to start taking measurements. You should have your pH meter with your application-specific electrode. If you have a refillable electrode, make sure that the electrolyte fill level is at least half an inch from the fill hole or closer. Check the electrolyte for contamination and refill it with more electrolyte if necessary. You'll also need buffer solutions. Standard calibration buffers are 4.01 pH, 7.01 pH, and 10.01 pH. Depending on your sample, you may need different buffers. When calibrating a pH electrode, it's important to choose buffers that bracket the expected reading. For example, if the expected reading is pH 5.2, then it would be best to calibrate to pH 4.01 and pH 7.01. If the expected reading is pH 3.2, then it would be best to use a pH meter that allows for custom buffers. You'll also need containers or beakers for calibration buffers, rinsing the electrode, and waste. You'll also need deionized water and a rinse bottle. Some nice-to-haves are an electrode holder and a magnetic stirrer. The electrode holder reduces the risk of breaking your electrode. A magnetic stirrer keeps the sample stirring to speed up response time, improve accuracy, and increase stability. Calibration is an important step to ensure you're getting the most accurate readings. You should always calibrate after a long period of disuse, after rehydrating a dried out electrode, or after using a cleaning solution. We recommend calibrating daily for best results. However, if high accuracy is not crucial to your measurements, it's okay to calibrate once or twice a week. Here's an example of a 2-point calibration using a basic pH tester. For this tester, we will stir manually. The things you'll need for this calibration are clean beakers for your pH 4.01 and 7.01 buffers, a beaker for your rinse waste, a DI water rinse bottle, and of course, your pH tester. The first thing you want to do is rinse your electrode with your DI water. Enter the calibration mode on your tester and place it into your pH 7.01 buffer. Stirring gently helps the tester to stabilize and get a more accurate reading. Once the reading stabilizes, rinse the tester again and place it into your pH 4.01 buffer. Once that reading stabilizes, notice how the tester saves the calibration points and returns to measurement mode. The next example we'll show you is calibrating a portable pH meter. This meter is a bit more advanced and typically has a separate glass pH electrode. For this calibration, you'll need your beakers for clean buffers, your waste beaker, a DI water rinse bottle, and your portable meter. First, remove the protective cover from the electrode bulb and rinse the bulb in DI water to remove any salt crystals left over from the KCl storage solution. It's completely normal for salt to build up around the base of the electrode cap. This electrode is refillable, so you need to make sure that you remove the fill cap so that the electrolyte flows out of the junction to close the circuit. Now you're ready to start calibrating. Enter calibration mode on your meter, rinse the electrode, and then place the electrode into your pH 7.01 buffer. Stir gently and wait for a stable reading. Once the reading stabilizes, rinse the electrode again and place it into your pH 4.01 buffer. Remember to stir gently when doing this calibration. Once stable, this meter returns to measurement mode and you would be ready to begin testing samples. Before we get into sample preparation, let's take a look at a typical lab setup using a benchtop pH meter. These meters offer high accuracy and dependability and can typically read between the hundredths and thousandths place. We'll do a 2-point calibration. The things you'll need to do this calibration are clean beakers for your calibration buffers, a waste beaker, a DI water rinse bottle, a magnetic stir, stir bars, and an electrode holder. The Edge pH meter comes with an electrode holder, making this a great benchtop option. Fill 2 beakers with enough pH buffer solution to cover the electrode junction. Add a stir bar to each beaker if you're using a magnetic stir. First, remove the protective cover from the electrode bulb and rinse the bulb in DI water to remove any salt crystals left over from the KCl storage solution. This electrode is refillable, so you need to make sure that you remove the fill cap so that the electrolyte flows out of the junction to close the circuit. Then place your pH 7 beaker on the magnetic stirrer. Start stirring. Make sure you do not stir too aggressively or have the magnetic stirrer set too high. The bulb and junction need to be fully submerged with no air breaking the contact. Here's an example of a stir set at the right speed. Notice there's no vortex. Enter calibration mode on your meter and lower the electrode into your pH 7.01 buffer. Once the reading is stable, it will prompt you to press confirm. Press confirm and the meter will save the calibration point and ask you for pH 4.01. Turn the magnetic stirrer off and rinse the electrode over your waste beaker. Place the pH 4.01 beaker onto the stir and begin stirring. Lower the electrode into the buffer and again, wait for the reading to stabilize. Once stable, press confirm. This meter can do up to 5 calibration points. In between each calibration point, remember to use your waste beaker and rinse the electrode with deionized water to prevent cross-contamination of buffers. To complete the 2-point calibration, we'll press the Cal button again, and it will save and store both calibration points. Once you're done calibrating, give the electrode a final rinse before measuring your sample. There are many different types of samples, and some require preparation before measurement. In this video, we'll be testing the pH of regular tap water. In this case, all you need to be sure of is that there's enough sample in the beaker to cover the reference junction on the electrode. You can check out some of our other videos on the preparation of cheese samples, soil, wine, and others. Okay, now we're ready to measure our sample. We have a few setups. The tester. Gently insert the end of the tester in the sample. Gently stir, like this, keeping the junction submerged. The portable. Gently insert the electrode, making sure that the electrode junction is submerged. The lab meter. We have our sample in our beaker, with a stir bar, on our magnetic stirrer stirring without a vortex. With everything in place, slowly insert the electrode into your sample and wait for a stable reading. It seems like a lot of steps to get that really quick measurement, but I assure you, for accuracy and repeatability, you need to take these steps. We aren't quite done yet though. Once you're done with taking measurements, you need to clean and store your electrode. This not only ensures that your electrode will continue to have a fast response time and provide accurate measurements, but it also maintains a longer life for the electrode. To clean and store the electrode, rinse with deionized water. We recommend using an appropriate cleaning solution after rinsing to remove any materials that may be left on the electrode. Let it sit in the solution for 15 minutes with the junction covered. After, fill your electrode cap with storage solution and fasten it onto the electrode until you're ready to measure again. If you have a tester like this, fill the cap. It's a good idea to store upright so that the stored solution does not leak out. Remember, the electrode should always be fully submerged in storage solution when not in use. That's it, 9 critical steps to understanding pH, choosing the right meter and electrode, and properly taking measurements. If you're curious about how to test more complex samples, subscribe to our channel to get updates as we introduce more videos on how to use a pH meter.